A Boeing weighing over 400 tons lifts off the runway, yet hidden inside each wing sits a controlled inferno. That inferno burns hot enough to melt almost any metal you could name, yet somehow the engine never warps or fails. How can one machine contain heat that destroys steel while spinning thousands of times each second without tearing itself completely apart? The answer hides inside 30,000 tiny parts, each built separately, then joined into a single flawless machine that defies belief. So how do factories actually build something this extreme, where one wrong measurement could cause a disaster far above the ocean? Let's walk through the hidden journey of a jet engine, from raw fiber and molten metal to a finished flying machine. To understand the genius here, we first need to grasp just how brutal the world inside a running engine truly becomes. Air gets squeezed, fuel ignites, and gas temperatures climb past 2,000 degrees, hot enough to soften the strongest ordinary materials. Inside that storm sit blades that must spin for thousands of hours, while everything around them tries violently to rip them apart. The first challenge sits right at the front, where a giant fan must pull enormous air in without weighing far too much. Take the blades from solid metal, and they grow too heavy, dragging the engine down and burning fuel the airline cannot afford. So engineers reach for a surprising solution, building these massive blades not from steel, but from woven layers of carbon fiber. Thin sheets, each barely thicker than a playing card, are stacked in precise directions, sometimes more than 1,000 layers per blade. Those layers get woven into a three-dimensional shape, then pressed and cured until they form one solid, incredibly strong, lightweight piece. The finished blade ends up roughly a third lighter than metal, yet still strong enough to survive years of brutal punishment. But here's a problem you might not expect, because the front of an engine faces constant attacks from the outside world. At full power, the fan swallows rain, dust, and even birds, all striking the blades with shocking and dangerous amounts of force. Can you spot how engineers prove a blade is ready before trusting it with hundreds of human lives high above the clouds? Each blade is scanned with ultrasound, X-ray, balance checked, and measured everywhere, then fired into violent impact tests that mimic real strikes. Building just one of these blades can take hundreds of continuous hours before it ever earns the right to enter an engine. Once finished, each blade slides into a central disc, locking into slots machined so precisely that almost no gap remains anywhere. This matters enormously because spinning past 3,000 times each minute generates centrifugal forces strong enough to tear loose parts away. Even a tiny weight difference between blades can create vibrations powerful enough to shake and slowly destroy the entire spinning engine. So technicians balance the whole assembly repeatedly, measuring forces and alignment until the fan can spin smoothly and safely for years. Once spinning, this fan alone pulls tons of air inwards every second, feeding the hungry core that generates the aircraft's thrust. But the fan you can see is only half the story, because the real magic happens deeper inside, hidden from view. Buried in the hottest zone sit the turbine blades, small parts that must survive temperatures that would melt almost anything else. Here's the puzzle, because these blades sit inside gas hotter than their own melting point, yet they refuse to melt away. The secret is hidden cooling channels, tiny tunnels carved inside each blade, letting cool air flow through and protect the metal. To form those channels, factories first shape fragile ceramic cores, then build a wax blade around them as a temporary model. That wax shape is coated again and again in liquid ceramic, slowly building a thick, hard shell around the entire pattern. That ceramic shell is dipped over 7 times, growing thick enough to hold molten metal without cracking under the intense heat. The wax is then melted out, leaving a hollow mold into which glowing molten nickel superalloy gets carefully and slowly poured. That slow cooling is critical, because the way the metal hardens decides how well the finished blade resists heat and stress. Once solid, the ceramic shell is shattered away, and the cores inside are dissolved, finally revealing those hidden internal cooling passages. Each raw blade still needs grinding, precise shaping, protective coatings, and hundreds of microscopic cooling holes drilled using sparks of electricity. A thin thermal barrier coating is added last, acting like sunscreen for metal, shielding each blade from the surrounding furnace heat. Every blade then faces X-rays, ultrasound, and airflow tests, because a single hidden flaw could trigger catastrophe miles above the Earth. Today, engineers are pushing even further, using metal printers that grow turbine parts from fine powder, one microscopic layer at a time. A laser melts each thin layer precisely, repeating thousands of times, building cooling shapes too complex for any traditional manufacturing method. When finished, dozens of blades are fitted around a disc, yet no two ever weigh exactly the same after all that processing. So every blade is numbered, and engineers know precisely which one belongs in which slot to keep the whole rotor perfectly balanced. Spinning past 10,000 times each minute, even a few grams out of place could violently shake the engine into total failure. Now the biggest stage begins, as thousands of separate parts from across the factory finally converge toward one single assembly line. Cranes lift heavy modules, the compressor, combustion chamber, turbine, and casing, slowly stacking them along one central shaft dozens of feet long. Inside the compressor, incoming air gets squeezed to more than 40 times normal pressure before it ever reaches the burning chamber. Throughout assembly, engineers obsessively check alignment and clearances, because even a tiny misalignment could destabilize the entire machine once it spins. Then come the support systems, as fuel lines, oil pipes, and hundreds of sensors are wrapped carefully around the engine core. Those sensors feed a control computer, often called the engine's brain, watching temperature, pressure, and speed in real time during flight. All those wires and pipes are locked down with vibration-proof mounts, because constant shaking would otherwise loosen connections and cause failures. And here, finally, is the answer to our opening mystery, because nothing about this engine is left to luck or chance. It survives its own inferno because every layer, channel, coating, and measurement was engineered specifically to fight one relentless enemy: heat. Cool air, clever materials, and microscopic precision combine, letting a furnace fly safely while carrying hundreds of people across vast oceans. Once assembled, the finished engine is locked inside a test cell, where power slowly climbs while hundreds of sensors watch closely. Only when it stays perfectly stable under crushing load does this machine finally earn the right to hang beneath a wing. Building a single engine can take months, yet factories still produce thousands every year, each one worth as much as a mansion. Next time you fly, remember the quiet miracle hanging outside your window: a tamed furnace carrying you safely above the clouds. It took tens of thousands of parts and countless human hours just to make that incredible journey feel completely ordinary today. Thank you very much for watching, and I'll see you in the next video.